close out with today is long division of polynomials. And what do I mean? So now we're going to switch gears. These are two different aspects that we're going to need to analyze and find zeros of polynomial functions. Complex numbers is one of them. This is a totally separate topic. And let's look at an example. Say I had x squared plus 3x plus 7 all over x plus 1. And I want to divide, because this is equivalent to, x squared plus 3x plus 7 divided by that binomial x plus 1. Well, how do I do it? Well, you do it just like you did the long division of numbers. You might remember that process. If you had, 684 divided by, say, 3. And you set that up like this with your long division, 684. Okay, what do you multiply the 3 by to get a 6? You do that 2. Come here and you do that multiplication, and then you subtract. So that's gone, and you kind of bring down that and you subtract. Right, so in this case, you subtract and then bring down the 8 then. And then 3 goes into 8 how many times? Well, that goes in another 2 times. I put down the 6 and subtract, and then I bring down the 4. And then 3 goes into, I worked it out nicely. I didn't even realize to do that. So 3 goes into 24 8 times precisely, so I get a 0 remainder. Now, what if I change this to 685? I just want to be a little bit over here. What would I do then? Well, in this case, I'd have 228. I'd subtract and I get a remainder 1. So how would I write my answer? The answer would be written as 685 thirds is equal to 228 plus my remainder over my divisor. Well, we're going to mimic the same long division of numbers with polynomials over here. So let's see how we're going to do that. So let's set this up as a long division type of problem. So I get my x plus 1 going to x squared plus 3x plus 7. Okay, so let me get rid of this. That's eventually, well, I'll put it up there. This one a little bit higher. X squared plus 3x plus 7 over x plus 1. I don't want to mix everything. Now I just key in on the x squared and the x. What do I multiply x by to get an x squared? Well, obviously x. So I'll do that over here, and I'll line up the x's. I won't put it to the front. I'll line it up right up here. That's what the x is. So then I do that multiplication, x times x plus 1, so I get x squared plus x. And just like over there, I subtract everything from what's above it. X squared minus x squared, there is no x squared. 3x minus x gives me 2x, and then I bring down the plus 7. Now I look at 2x and x. What do I multiply x by to get a 2x plus 2? Do that multiplication. Just as I'm multiplying over here as I go through each of those steps. This gives me a 2x plus 2, and I subtract by what's above it. Well, 2x minus 2x gives me 0x. 7 subtracting 2 gives me 5. So what is my answer? Well, this expression here is equal to x plus 2 plus my remainder, which is 5, over my divisor. And that's long division. Now, there are some twists along the way when you might have fractions or when you're missing a term. I'm going to do those on tomorrow, because this section we actually do over 2 days, so we'll do that more in line with tomorrow. But let me give you one basic one to try as we close this out. And try this on your own. I'll make all these positives for now to make this first one easy. You can try some more in your homework. So try this one.
So do that by long division and see what you get. And I'll try and do it in my head and see what I get. Oh, make this, I'll leave it that way. I'll make this a 10. Well, I'll do it that way. Leave it a 9 and you'll see what you get. You're going to get a 0 remainder. My brain works mysteriously. That means x squared plus 6x plus 9 factors into x plus 3 times x plus 3. But you get 0 remainder, so you don't have to write anything. Or in this case, you could have factored that. I guess my brain was doing that without me thinking about it, because notice that's a factor. So sometimes you can do it without the long division. If it's a perfect 0 remainder, quite often, however, you cannot. That sometimes just happens. But you can also do it with the long division, and you get the same thing, but you just get with a 0 remainder. I guess my brain already computed that. Okay. So we learned two different things today. Complex numbers, complex, and what goes along with that is complex arithmetic. And we started with this idea of long division. We're going to do this over today and tomorrow because some more of the different thing on. This is more long division, where we're going to be looking at some of the more complicated aspects of it. It's the same process, but how you handle it can be very important. So we're looking at 9x squared minus 5x plus 1, and we're dividing into that the binomial 3x minus 1. Okay, so what do? We set it up like a long division problem. And we have our 9x squared minus 5x plus 1. So we start by considering the 3x and the 9x squared. What do I need to multiply 3x by to get 9x squared? 3x, because 3x times 3x is 9x squared. So I'll place it here. And I'll multiply this expression by that. So that will give me the 9x squared subtracting 3x. And then what I'm supposed to do after this is to subtract the result. So I turn around here and I subtract it. So I get 9x squared minus 9x squared. That's what I chose, the 3x, because that term vanishes. This becomes a positive 3x, and that becomes a negative 5. So I want to add a positive 3x to a negative 5, and that regard, I get a negative 2x. So minus 5 plus 3, because I'm changing the sign of that. And then I turn around here and I bring down 1. Now this is where I get a little bit problem, because I have a fraction. So I want to multiply 3x by something to give me a negative 2x. Well, the x is already there, so all I have to do is multiply by a negative 2/3. What I'm doing is this. I want to take 3x times what gives me a negative 2x. That's what I'm trying to do, figure out. Well, I can get rid of the x's. So 3 times what is equal to negative 2. Well, of what is just negative 2/3. So we're back to fractions again. So that's what I'm going to put over here. Let me do that a different color so we can kind of see that. I'm going to be doing a negative 2/3. So I'll multiply a negative 2/3 times 3x minus 1. Well, when I distribute that, that's going to give me a negative 2x, exactly what I wanted. And negative times a negative is going to give me a positive 2/3. But what do I want to do? I need to subtract that result. Okay, negative 2x minus a minus is going to be positive 2x. This is 1, subtracting 2/3. And that gives me a remainder then of 1/3. This is really 3/3 minus 2/3, so it's my remainder of 1/3. So what is my answer? Well, this expression here, let me put it over here. So what I'm saying is this. 9x squared minus 5x plus 1 over 3x minus 1 is equal to 3x minus 2/3 plus now my remainder over my divisor. That's one way of writing it. You could actually rewrite it if you're comfortable with your algebra and your fractions. You should be trying to manipulate these things in many different ways. This is fine, but you might also see this. That's equivalent. Make sure you understand the algebraic equivalence of various expressions, because you'll see that a lot. The better you are at manipulating them, the more practice you'll have with the algebra, the better you'll be in your calculus. But that's the next twist. Sometimes it's just not integer values that you're multiplying by, it can be fractions. So you have to play around. You have to be comfortable with fraction arithmetic. Okay, so let me give you one to try on this. Yes, Ashley.
Hi, Professor. You had a different answer in the book. Can you just show how you got that? Show how you manipulated it to get it that way?
So I have, what, a different answer in the back that's, make sure it's correct, because hopefully, let me just see what the answer is. This is correct here. I want to double check that. I was rushing to get some of these things out. Oh yeah, okay, so it's the same thing. There's a typo. A little typo there that should have had a 1 over there. So it should be x minus 1 for number 9. Glad you caught that. So there's a typo there. I'll correct it now. I'll show you what the typo is. I can see that right now. Especially when you're typing these things into the math processor. So what it should have said was this. This first part is the same. I could factor out a 3 over here. So I could put this over here as 3, and then I'd have 3x minus 1. The typo was in the textbook, this is a 2. It should have been a minus 1 over here, not a minus 2. So that's a little typo there. But everything else is correct. That's just a typo in the answer key. So good, catch me on this thing. That's what I'm trying to do. Because I rushed over the summer to do these things, and I was trying to get it out to hit a deadline so that they could be printed and everything. And it was a little bit crazy. I'm glad you caught that, so I can correct that one. But the takeaway here is now sometimes the factors we use are fractions. So get comfortable with your fraction arithmetic. And the more you do it, don't just rely on your calculator. They have that nice little button on the calculator, the FRAC button, and students say, oh, I don't need to know fraction. It comes up in all these other aspects of mathematics, the whole concept. Understand the concept. Don't rely on that little button that'll always give you that decimal to a fraction. It's a nice little tool, but it actually, hinders you more than anything else. It doesn't help you, because that means the calculator can replace you if you're not able to think through. They don't need you. They don't need to pay you. They can just buy a cheaper calculator and don't give you the salary. They just have somebody else press the buttons and the answers are there. Understand the concept. It's good for correcting yourself and double checking, but understand the concept. Don't rely on that as a crutch so much. Just as a check. did you get the concept? You had the concept right, and did you make a little typo or mistake? Okay, so that's one aspect. Let me give you guys one to try again. We'll have fractions in it. Maybe I'll put a complicated one that's going to have fractions at the beginning. And now, you may make mistakes. It may not be perfect, but I can look, because I'm going to be looking at your work. I'm not going to be looking at a multiple choice answer that you can kind of guess your way through. So I will see, do you understand the concept? And maybe you're just making a simple mistake. Now, sometimes the simple mistakes are really something that is conceptually a mistake. It may look simple, but it's really the concept is not right. And I've been doing this long enough that I can pick that out. I'll make one up over here on my top of my head and get you guys to try this. So try that one. Set it up, and then I'll go through it. You try it on your own. It's going to be a fraction right at the get-go. You can see fractions on top of fractions here. So let's see what we get for that one. Start to set it up. Take this for given. I'm just doing it in my head and see without doing anything. So make sure everything comes out okay. I'm not sure, but I think it could be this. Could easily have made a mistake here, so let me just see. Oh, I could, if I wanted to, write this as. Not sure about this, because I'm not writing anything down, doing it all in my head, so could easily make a mistake, but we'll see. See if I got close or not. Okay. Could be off here, but this is what I got doing in my head. Does anyone want to see this worked out? Okay, so the first thing we need to do is match up the 2x with the 3x squared. So I'm looking for a factor to do that. I'm looking to take 2x times what will give me 3x squared. Okay, well I can get rid of the x right away. So I just, in this case, divide both sides by 2, so the unknown I'm looking for is 3 halves x. That's exactly what I have here. So I'm going to multiply both sides by 3 halves times x times 2x minus 1. So this will give me, the 2's will cancel, so that will give me a 3x squared, and that's a negative 3 halves x. And what am I supposed to do? I'm supposed to subtract everything. 3x squared minus 3x squared is gone. So this is a negative 2x plus 3 halves. So that gives me a negative 1/2 x. So here I get a negative 1/2 x, and then I bring down the plus 2. And hopefully we're okay with that. Now I want to do the same thing with this negative 2x and that. I want that to be the same. So let's do that on the side. So 2x times what will give me a negative 1/2 x. Well, I can get rid of the x's. Divide both sides by 2, so that unknown is negative 1/4. So that's what I'm going to do. I'll multiply that expression by negative 1/4 times 2x minus 1. Well, that will give me what I want. 2 over 4 is a negative 1/2, and that will give me plus 1/4. But I'm going to subtract everything there. 1/2 x, excuse me. So negative 1/2, pi 1/2 is gone. 2, subtracting 1/4, that gives me, 2 is 8/4, subtracting 1/4 gives me 7/4. Okay, so my final answer then is that 3 halves x minus 1/4 plus 7/4 over 2x minus 1. Well, I can rewrite that as 3 halves x minus 1/4 plus 7, and I can just put the 4 in the denominator, 2x minus 1, or 8x minus 4. Yeah, so I was okay. I can easily make mistakes when I do that. But you can see where knowledge of fractions enables you to get through these. It can be complicated. But it actually trains you in your algebra. Fractions are a good training in algebraic manipulation. Okay, so that's a random one I just made up and we solved that. Okay, what are some of the other aspects of it? Well, let me just, out of curiosity, since I can't see your faces, how many people either got the right answer or got close to the right answer? There's a couple of people there. So maybe about half of them, just under half of the class. So let me try another one, since we're not quite there. Try one more before we do the next level of complexity regarding these long division problems. As I can see, we need a little extra assistance here, so I'll give you one more to try before we look at the next one. So try this one. So I'll make this a little bit easier. I'll start it out a little bit easier. So try that. It doesn't turn out to be too bad. I don't think it has fractions in it. I had to think about it a little bit more. Definitely I'm not sure about this one, but that's what I'm doing in my head. I don't know if I got it right or not, but we shall see. Okay, does anyone want to see this one? Am I getting close doing it in my head, or let's give it a try and see what happens over here. First part is relatively easy. I want to end up with a 4x squared, so I just multiply everything by 2x, so let's do that multiplication. So that gives me a 4x squared plus 6x, and I am subtracting everything. So when I get negative 5, negative 6 is me a negative 11x, and then I bring down the plus 3. Okay, now I have to have 2x times some factor has to equal my negative 11x. Well, I can get rid of the x. It's not going to be a factor, no pun intended there. And I just divide both sides. Ah, that's why I flipped it over. It's supposed to be, yep, I flipped it over in my head. So my unknown is minus 11 halves. Yeah, it makes sense. So this should have been minus 11 halves. Because that's what I'll do over here. And when I do that, so that changes. The last thing definitely changes as well, too. So now I minus 11 halves times 2x plus 3. Well, when I multiply that, that will give me exactly what I want. Minus 11x. And this is going to give me negative 33 halves. And I'm going to subtract them, so that'll become positive. This is another 6 halves. So when this subtracting that gives me 39 halves. So this would be 11 halves. I knew there was I flipped that in my head, but it's a good try. And 39 halves. This is my positive 33 halves. 3 is 6 halves. 33 plus 6 is 39 halves. That's my remainder. So it's always my remainder over my divisor. So that's why I flipped it a little bit there. Okay. These are hard. These are hard because you have to work with the fractions. A little bit easier if I'm writing it out, but that's why I try to do it in my head to see how well I can do it. It's comparison for you guys working. Okay, let's take a look at the last added complication. What happens when you're missing a term? Now you just have to be careful. The way I like to treat it is by putting that term in with a 0 coefficient. So let's take a look at another type of problem. So the last complication is, what if you are missing in either one, missing a term? Let's start with missing a term up in the numerator part. Say I have 3x cubed minus 2x plus 5. I'm going to divide that by, let's make this a simple one, x plus 3. Well, if I set it up normally, you might see a little bit of a difficulty over here. When I multiply this by 3x squared, I'm going to get a 9x squared. So it almost will look like I tried to be subtracting squares from x terms. What I like to do is to set it up so I put in all the missing terms with 0 coefficient. So it's just bookkeeping, if you will. So I would write this as plus a 0x squared. Then I'd put my minus 2x, and then I'd put my plus 5. Why do I do that? Well, I start out by what do I multiply x by to get my 3x cubed? Well, it's a 3x squared. So I multiply that. So that gives me my 3x cubed plus 9x squared. Now, if I had the minus 2x over there, some people might just try and subtract the x squared from the x term. But this avoids the problem. Next step is you subtract. That gives me minus 9x squared. and then I turn and bring down the negative 2x. So what do I multiply x by to get a negative 9x squared? Well, in that case, it's a negative 9x. Okay, so I do that. Negative 9x times x plus 3 is a negative 9x squared minus 27x. Okay, but I'm subtracting. So this is 27 subtracting 2x gives me a 25x, and then I bring down the plus 5. And then what do I multiply? Well, I now multiply by 25 to make that work out. I put plus 25, do the multiplication, so I get 25x, 25 times 3 is 75. Subtract this, and I get negative 70 as my remainder. So the answer to this problem over here is that this simplifies to 3x squared minus 9x plus 25 plus my remainder. I'll just write it as minus 70 over my divisor. I do not like you just to write the answer remainder negative 70. I don't want that. I want to see the algebraic equivalence. So in this case, I don't like this, and I don't use this, that, and remainder negative 70. I wouldn't do that. Don't like it at all. Because it blurs the fact of what you're actually doing. I think that whole notation should be banned from secondary schools. What are you actually finding? That's what I'm finding. Because it blurs what you actually did over here. Now the remainder sometimes is very important. In the old days it was used because without calculators, there turned out to be the simple way of being able to evaluate this. I mean, that's the same result I would get if I took this polynomial here and plugged into that x equals to negative 3, did all the arithmetic, I'd get negative 70 out. That's the old-fashioned calculators that they were able to develop pre-electronics days. But since we don't use that anymore, it's an antiquated notation, and we have to learn so many things, so that should go by the wayside. That's the other reason why I do not teach synthetic division. Nothing wrong with synthetic division, but it's a tool that was used pre-calculators. We can do the same more quickly with the calculator, meaning evaluate a function. I'd rather spend more time on the other topics so you understand those rather than something that I can do on a calculator. It doesn't give you any extra added meaning or understanding of something. So this whole problem here could have been done with synthetic division because it had a 1 in front of it. I don't like that technique because it's limited. Long division works for everything, and it will come up over and over again. You'll see it in calculus 1, 2, 3, etc. It's all the time. You have to rechange or take a rational expression or rational function and then rewrite it as a polynomial part and then a rational expression part. Okay, so let me give you one to try, and we will end with that. I'll also make this with a 1 in front. Now, it could be that maybe I'm going to divide this, third degree polynomial by a second degree. It could be I might have x squared, minus 1, and I'm missing an x term. What would I do? I'd put the 0x in the divisor as I'm multiplying and dividing it out. That way I'm just lining up the right polynomial terms, term by term, so I don't subtract from the wrong part. Just an easy bookkeeping approach. So we'll end with this, with the short class today. Let's try this one. Let's set that up and see what you get.
know how to do it next time. I'm not sure about this, carrying in my head, so don't know if I did it right, but we'll see. Does anyone want to see this one worked? Okay, so let's do the whole process over here. See how close I got or not. Okay, so again, I'm focusing on, I'm missing an x term, so I will put it over here with the 0 coefficient. That way I'll line things up correctly. The cubes, the squares, the x's, and the constants. Okay, first step, look at that. What do I need to multiply x by? Well, 5x squared will do, so I'll do that multiplication. So I get my 5x cubed minus 10x squared, but I subtract. So it becomes a plus 10x minus 2x, plus 10x squared minus 2x squared gives me an 8x squared, and then I bring down the 0x. What do I multiply x by to give me 8x squared? Well, it's an 8x. So that's what I'll put over here. And I do that multiplication, 8x times x minus 2. So it's 8x squared minus 16x, but I subtract. So that becomes a positive 16x, and then I bring down the plus 1. That's where I made my mistake. So over here, my next thing, that should be 16. I was adding the 1 in my head. So I'll do that multiplication over here, x minus 2. So 16x minus 32. What I'm subtracting, so it becomes a 32 plus 1 is 33. So that's the other mistake. I did 17, double that. So I should have a 33 over here. That's my remainder. Then I put my remainder over my divisor, and I'm done. But that's all. That shows you the complexity of this long division technique. Now, the long division technique, we're going to talk about how it's useful when we started to find what we call zeros of polynomials. That's going to be the focus of us, finding something called a zero of a polynomial. And we're going to find that zeros can be both real numbers, they can be complex numbers, and they come in a certain relationship if they are complex numbers. So we automatically know that by something called the fundamental theorem of algebra, which you may or may not have seen in a previous course. And we'll talk about that because that comes into play when you start looking for solutions to where your function crosses the x-axis. And that's what we call a zero. We'll talk about that. But any questions on this? Hopefully you're getting a little bit better about the algebra associated with the long division process. There's the simple problems, and then there's some other complications. These are the more of the complications that are added. Fractions always become a complication. I avoided the fractions on all of these simply by putting a 1 in front of that x over here. If I had anything over there, there's potential to have fractions cropping up all throughout. If you see division, that's the first coefficient is something other than a 1 that doesn't go in evenly, you might start out with fractions or they could develop later on. So be comfortable with your fractions.